Hi everybody. Hi everybody. I got tired of making these videos from my house, so I decided to go to Hogwarts. Having a good time here. Uh, and I want to show you a video. Speaking of awesome things, ow! I hit my head on the chandelier. It hurts. I want to show you. I made a little video. We had such a starting discussion of mathematical induction that I want to give another example. So let me share screen. There we go. Now, there you go. Alrighty. Now we'll share. Taking a very little time with it. Okay, sharing screen. So I'm hoping you guys are all seeing this, and now we're going to do some. We're going to look at proofs. So I'm going to prove here that 1 squared plus 2 squared plus 3 squared dot plus n squared is equal to n times n plus 1 times 2n plus 1 over 6. And so first, let's just look at a couple of examples. So step 1. Let's look at it. Now, the truth is, I'm going to show you 3 examples. Really, I just have to show you one and done. But, you know, what can I say? I'm a great guy. So 1 squared is equal to 1 times 1 plus 1 times 2 times 1 plus 1 over 6. And that comes out to 1 times 2 times 3 over 6, which equals 1. So 1 squared equals 1. Yay. Now, I could stop right there. But just for fun, let's just take a look. 1 squared plus 2 squared. Well, according to the formula, which I'm trying to prove, that should be 2 times 2 plus 1 times 2 times 2 plus 1 over 6, which comes out to 2 times 3 times 5 divided by 6, which comes out to 5. And that indeed is 1 squared plus 2 squared, because that's 1 plus 4, which is 5. And let's just do one more example. 1 squared plus 2 squared plus 3 squared. So according to the formula, that's 3 times 3 plus 1 times 2 times 3 plus 1 over 6, which is 3 times 4 times 7 divided by 6. And that comes out to 14, which indeed is the sum of those 3 squares. 1 plus 4 plus 9 does add up to 14. Now, so like I say, I did more than I had to do. Really, all we have to do is just show one case. I showed you 3 cases just because I wanted you to get the feel of the formula. But how are we going to prove this with induction? So we want to show that whenever it works for a number n, it will also work for the next number n plus 1. It will automatically work for the next number n plus 1. And if we could show that, and we already know that it works for n equals for 1, for n equals 1. Well, for us for n equals 1, then it automatically will work for n equals 2, because that's n plus 1. And if it works for 2, it's going to work for 2 plus 1, which is 3. If it works for 3, it's going to work for 3 plus 1, which is 4. If it works for 4, it's going to work for 4 plus 1, which is 5. And on and on and on and on forever. And basically, I'm going to wind up getting all the positive integers. And I keep saying it's sort of like a domino effect. When I say domino effect, you know, if you ever make a stack of dominoes, you push them over, each one knocks the next one until it goes all over, you know, until it knocks them all down. Anyway, let's see how to do this. So we have 1 squared. So we're going to look at 1 squared plus 2 squared dot plus n squared plus n plus 1 squared. Now, we're assuming that n is a number where this formula works for. So that means the first part of this, the 1 squared through n squared, that is equal to n times n plus 1 times 2n plus 1 over 6. We call that the inductive assumption. I mean, we're assuming we have such a number n where this works. Actually, we know we have it because we've shown that it's, we've already established that it works for 1 and 2 and 3, but whatever. Call it the inductive assumption. Anyways, I want to add that on to n squared. I'm just bring down the n squared, but I want to combine these 2 suckers, so I need a common denominator. So I multiply the second fraction by 6 over 6. I wrote the 6's in red to show that that's, the original thing was n plus 1 squared, and I'm adding in the 6's. Anyway, what I want to factor this guy here. So if you notice that these two fractions, each of these two fractions has a factor of n plus 1. By the way, you could do this any way you want. I just find it easier factoring out the n plus 1. So I have two fractions here. And I'm going to factor out the n plus 1. So now I have, and of course I combine the two fractions. So I have n plus 1 times what's left, and on the left fraction, what's left is n times 2n plus 1 after I remove the n plus 1. And on the other fraction is 6 times n plus 1 to the first power. And now I'm just going to distribute out the parentheses, and I get 2n squared plus n plus 6 plus 6n plus 6, 2n squared plus n plus 6n plus 6. And then that, of course, becomes n plus 1 times, in brackets, 2n squared plus 7n plus 6. And I could factor the 2n squared plus 7n plus 6 into n plus 2 times 2n plus 3. So altogether, all told, I now have this guy. This is now equal to n plus 1 times n plus 2 times 2n plus 3. And this we're basically done, because this really is the formula. If I would substitute n plus 1 for n into the formula, and just to see it more, I just wrote it again this way. I wrote it this way just to show that this is like plugging n plus 1 into or substituting n plus 1 in for n to the formula which I'm trying to prove. The formula I'm trying to prove is the one way up on top. Anyway, back here. So we've shown if it works for one number, I mean, if the formula works for one number, it will work for the next number. I mean, if it works for if I could find a number n that it works for, it'll work for the next number after n. Now I know it works for the number 1, hence it will also work for number 2. And if it works for 2, then it'll work for 3. If it works for 3, then it'll work for 4, and on and on and on and on and on. And that will eventually hit all positive integers. So this formula will be true for any positive integer. QED, quand ergo demonstratum, or something like that, which means thus it is shown. And that concludes all I want to do in this little video. Now I'm going to sign out, and we're done. But first I gotta stop the recording. If you receive an email, okay.